Hi, this is Mrs. Peachy from your WCA astronomy class, and today I'm going to be doing the last of my podcasts, and this one is going to be on the life cycle of large mass stars. So one of the things we've been talking about the last several podcasts, and if you have not seen the other two, I would highly recommend watching them before watching this one. We've talked about how we can kind of compare a star's changes that it goes through from the time that it is formed until it runs out of fuel, as we can kind of use it as an analogy to the life cycle of people. So that's what this slide is kind of showing you. It's kind of showing you that as a star is forming, it's kind of like a baby who hasn't been born yet. And during the time in which the star is actively fusing hydrogen and making helium, it's kind of like in the main part of its life, a time where it's growing and forming into a fully functional adult. And then it starts to age, and that aging process isn't pretty. It actually, you see a lot of changes occurring like you would when you are in middle age, like the red giant and supergiant stars show. And finally, when you get to old age and death, you are a white dwarf and black dwarf star. So those are the types of stages. So stars that we'll be talking about today are larger mass stars, and larger mass stars will appear blue to violet in color. They are higher temperature, just like we can see this end of the spectrum is higher in temperature, and therefore, and they're also higher in mass, so they're bigger stars. Let's see if I can find a picture. It kind of illustrates to you the different sizes and temperatures of these stars. So these types of stars we're looking at are spectral types O, B, A stars. They're going to have surface temperatures in the tens of thousands of degrees Kelvin, and they're going to have core temperatures that range to several 100 million degrees Kelvin for the temperature in the core. Now this is due to the fact that these guys are just really, really big. Compare a spectral class G star, which is the sun, to a spectral class O star, and the difference in size is pretty astronomical. Haha. Pun intended, I guess there. So basically what's happening is that these guys, they're burning really, really fast. That hydrogen is converting into helium at a much faster pace. So even though they have more fuel, they go through it so quickly that their lives are very short. Compared to the sun, which has a lifespan of about 10 billion years, a big blue supergiant star is only about 10 million years, or 100 million years for a somewhat smaller one, right? And these are much more rare here because they are so large. The greatest majority of stars in the universe are actually these red dwarf stars, which make up 80% of all stars. They're low mass, low temperature stars, low luminosity stars as well. And they have very, very long lifespans, upwards of 200 billion years, so longer than the actual age of the universe itself. When stars start to grow and change due to changes inside of them, when they start to grow old, they change into these stars, giant stars and supergiant stars. And you can kind of see there, again, the difference in size is it's pretty astronomical, right? So that's the differences we're talking about. And let's look at exactly why this is occurring. And I did talk to you about this in the previous podcasts as well. But there's a special type of state that a star is in, and it is called hydrostatic equilibrium. And I'm gonna type that here for you guys. So hydrostatic equilibrium basically is referring to a state where the external pressure pulling that star together, that's gravity, pulls that star together, is equal to the outward force that comes from those nuclear reactions in the core. So the hydrogen converting into helium is an explosive force, and this is occurring, at an exponential level, but it's equaling the force of gravity. So the star remains very stable and doesn't change in size, right? And it's giving off heat and light and all sorts of different types of electromagnetic radiation. The other thing that's occurring is, you have this core that's made up of hydrogen, and that hydrogen is fueling into helium. After a while, though, all of that hydrogen in the core becomes used up. And when this happens, that's when we start to see changes. If you take away the arrows pushing outwards, and you only have those gravitational arrows pulling in, the star is going to shrink. And when it shrinks, it collapses, it gets much, much hotter, and it becomes much more dense, lots of pressure and heat. It becomes so much more pressure and heat that helium can now be forced together to fuse hydrogen. So that's occurring. So that is going to cause those outward arrows coming back again, so the star will then expand. And in addition to that, there's another layer of the star. If you go back, is this one? Nope. So what actually happens with these high mass stars is that you'll have helium fusing into carbon in the inner part of the core, but then you'll have another ring where hydrogen is still fusing into helium. So that's happening as well. So you've got now two levels of fusion going on in these high mass stars. So that's increasing those outward forcing arrows. So now it gets even bigger than it was before. And that's why you have these stars developing into red supergiants rather than just red giants. They become these big red supergiant stars. Now this process goes on and on. After a while, it's going to run out of helium. And then it will shrink again because, again, no outward arrows, only the inward pull of gravity, and it heats up even more this time. And it will now start to fuse that carbon into nitrogen, and now expands another time, right? And it keeps doing this over and over and over again. Hydrogen, helium, carbon, and oxygen and neon, silicon and sulfur. So we have all these different layers going on, and sometimes multiple layers are fusing at the same time. What eventually happens is you end up with a core that is made of iron. And this is a very, very dense core, okay? In fact, it's so dense that the iron core produces neutrinos, which are releasing from the core. These are basically just neutrons, right, that are moving. And protons and electrons combine to make more neutrons and neutrinos. And then we have the star collapsing, again, due to the loss of fusion. But because the core is so dense this time, you don't get the compression that you had before. Instead, you get this rebound effect, and it collapses and basically rebounds off that iron core and bursts outward in a supernova explosion, right? So that's what a supernova is. It says in a fraction of a second, a wave of matter forms a shock front that moves outward towards the stellar surface. The shock wave hits the surface of the star and explodes. The inward shock compresses remaining stellar core into a neutron star or a black hole. So then we need to ask ourselves, well, what does it become, a neutron star or a black hole, and why? Well, a neutron star is going to form from a bigger star, something that's about 1.5 to 3 solar masses, so bigger than the sun but not super huge. Anything that's greater than 3 solar masses will form a black hole. So let's talk about the difference between a neutron star and a black hole. So what we have here is one potential ending of a kind of medium-sized high mass star, and that is something called a neutron star. Now, a neutron star occurs when that last amount of fusion is done in the core, and the core or the star collapses under its own gravity. You do have the first rebound in that supernova explosion, right? But what's left over is that you have the neutrons of the atoms, but you also have the protons that have combined with the electrons to produce neutrons, but then they also produce neutrinos as well. These are some particles that are streaming away from the neutron star. Now, what happens as it collapses is it begins to spin faster than it was before. It's already rotating, just like all stars are rotating, but it spins faster and faster and faster the smaller it gets. Neutron stars can be between 20 and 10 kilometers wide, so not very big at all compared to an actual large mass star, right? But they are as massive as 1.5 suns, right? So they're really, really massive for their size. Just exceptionally massive. A teaspoon of a neutron star would weigh 100 million tons, to give you kind of an analogy there. So these are for your medium high mass stars. For the higher mass stars, ones that are greater than 3 solar masses, you end up with a black hole. Now, black holes are not directly observable. They aren't something you can see, because what happens in a black hole is that the gravity is so strong that in order to go fast enough to escape the gravity, you would have to travel faster than the speed of light, which is impossible to do. So not even light can escape a black hole. That's why it's called a black hole. Because nothing can escape a black hole. They can't directly be measured, but they do sometimes swallow neighboring stars if the star is close enough and in its gravitational field. And when that happens, oftentimes high frequency radiation is given off in the form of X-ray radiation. And so we have special telescopes that are equipped to observe an X-ray radiation. The Chandra X-ray Observatory does this and can take pictures of this energy as it is kind of just kind of being pulled into that event horizon of the black hole. Okay, so that is kind of the end of this part of the life cycle of stars. I do have a video that I would like to link you to in my description, because I believe it does a pretty good job of talking about neutron stars and black holes as well. And if you have any questions or concerns, feel free to give me a call at extension 2204 or send me a webmail message. Thank you.